All right, so let us start chapter 9. Your next exam will be after chapter 9, right? And chapter 9 is going to be a continuation of chapter 8. You need the Lewis structures here. Okay, after 9 we have exam 3, 7, 8 and 9, exam 3. And then we will have, a couple of sections from chapter 11, which I choose, like maybe 1 or 2 lectures, and then you will have your final exam.
Finals over everything?
Yes, and I'll give you a study guide for final.
Oh, thank you.
Do we have class next Tuesday?
Yes, we do.
When does break start? Wednesday?
No, break starts after Tuesday's classes.
Oh, thanks.
Not only for us, for everyone. After all Tuesday's classes are over, that's it. Wednesday, Thursday, Friday is a holiday. Yes, come back. All right, so this chapter is about molecular geometries and bonding theories. So we know how to draw the Lewis structure, but that's not actually gives us the shape of the molecule. The shape of the molecule means it's a three-dimensional picture we have to imagine. Lewis structure we are drawing on the sheet of paper, right? So it's only two-dimensional. But the actual shape of something, an object, it has 3 dimensions, so shape is going to be 3-dimensional. So now we are going to learn how we can decide the shape by looking at the Lewis structure. That's what this first part of the chapter is about. Now, first of all, why do we need to know the shapes? Because shapes of the molecules are very important, especially in reactivity of chemicals as well as in living system. If people who have taken the biology, any sort of biology classes, you know that like we in our body, human body has thousands of enzymes which don't interfere with each other. They do their thing, very specifically. How does that happen? The shape of those enzymes, that's what plays the major role in there, because each enzyme has a specific shape and the receptor for that particular enzyme has that accommodating shape, and when only those two match, things will happen. If somebody else just walk by, they don't fit into the shape. It's like the key and lock mechanism. Only the correct key will fit into a lock, right? The other keys, if you put it in, it won't fit. So it's like that. When the correct shape enzyme matches with the correct shape receptor, well, they would stick, and whatever the action is supposed to happen, that would happen. So in living systems, all these proteins and enzymes and all the stuff, the shape is very important. And in chemical reactivity also, the shape of the molecule become important. So now by noting the number of bonding and non-bonding electron pairs, we can predict the shape of the molecule. So here this picture actually shows you a couple of shapes which you will definitely see. You will have linear molecule, bent molecule, trigonal planar molecule, trigonal pyramidal molecule, T-shaped molecule. There are more shapes. We will see. There are more. This is just a couple of them. There are a lot more shapes we will see, and we are going to learn all of them. Don't worry, it's very easy once you get the basics.
This was stuff I didn't do too well.
It's not something you can memorize. Let me tell you that from the beginning, okay? If you are trying to memorize all the picture with, this molecule is this molecule is this, it will not work. It becomes too confusing. We are going to learn it the systematic way, so that any molecule you draw the Lewis structure and you can predict the shape. Okay? So we are going to do that. So what actually determines the shape of a molecule? Before we go into the shape detail, just a little bit theory, why the shape is different from the Lewis structures, or why molecule has these certain shapes. So simply put, electron pairs, whether they are bonding or non-bonding, they repel each other. We know that electrons are all negatively charged and same charges repel each other, right? So it comes from that basic principle. Electron pairs around the central atom or in a molecule, they are going to repel each other regardless of whether it is bonding or non-bonding. And you can imagine, if some electrons are put together and they are all repelling each other, they exist as pairs, and the pairs are repelling each other. So if they are repelling each other, they would try to take up positions as far away as possible from each other, right? If they are attracting, yes, they will stay together. Their goal is to stay as close as together. But if they are repelling each other, then they would take up positions as far away as possible from each other. And that is actually the basics of this different shapes arising. Why these electrons would take these different positions. So in order to do that, first we need to understand what do we mean by electron domains. So we can refer to these electron pairs, non-bonding or bonding, as electron domains. So the first step of predicting a shape is always drawing your Lewis structure. And after drawing the Lewis structure, we are going to count the electron domains around the central atom. When you do the count, this is the rule we follow. Every non-bonding pair or lone pair, that we count as 1. Every single bond, 1. Every double bond, 1. Every triple bond, 1. Even though double and triple bonds have more than 2 electrons, we count each bond as just 1. Okay? Single bond is 1 pair, double bond is 1, not pair, we should say set or electron domain. So single bond is 1 electron domain, double bond is 1 electron domain, triple bond is 1 electron domain, and the lone pairs, each of those pairs are 1 electron domain. This picture would make it clear to you. Here is a molecule, and let's say this is the Lewis structure. So according to this rule, if you count the electron domains around A, how many electron domains we can count? So this is 1, the lone pair, 2, 3, and the double bond is considered as only 1 domain. So we have total 1, 2, 3, 4 domains. Got it? Only on the central atom, yes. Yes, only on the central atom. When we come to the shape, only the central atom and the electron pairs around the central atom matters. Do not worry about the peripheral ones. Peripherals one will always have 8 electrons around it. Okay? And that's it. Once you have the Lewis structure, don't worry about the peripheral ones. Only the central atom matters. So once again, the central atom has 4 electron domains. So keep that in mind, even though you will be tempted to count the double bond and triple bond as 2 and 3 pairs, right? Actually, there are 2 or 3 pairs in a double bond and triple bond, but these are not the pairs we are counting. This we are counting electron sets. How many groups of electrons are there? That's what you are looking for, not the actual number of electrons. Everyone understand that difference? So here we are counting the electron groups around the central atom, and we count lone pair as 1 group, and single bonds as another group, double bond as another group, triple bond as another group. So in this molecule, you have 4 groups around. And why double and triple bond we don't count all the electrons? As it says, in a double or triple bond, all the electrons are shared between the 2 atoms, and they don't actually repel from each other. They all stay together as 1 group. All the 4 electrons in a double bond stay together as 1 group. All the 6 electrons in a triple bond stay together as 1 group. They are not repelling within each other. That is why we count them only as 1 group when you count the electron domains. Now, once you get the electron domains, well, this topic we just discussed, these electron domains, they repel from each other. This is called Valence-Shell electron-pair repulsion theory. Long name, so short form we call it VSEPR theory. Just the first letters of Valence-Shell electron-pair repulsion theory. So the VSEPR theory is basically put together in this one sentence. The best arrangement of a given number of electron domains is the one that minimizes the repulsion between them. Or in other words, the best shape is when the electron domains will take up positions which are as far away possible from each other. That would give you the shape of the molecule. That's what VSEPR theory is saying. So, how do we go about with this? Well, this is a table which contains the electron domain geometries for the 2 to 6 electron domains around a central atom. So, the first column is giving you electron domains. Let's say, you have molecules and you are counting those electron domains. And if there are 2, then it's called linear. If there are 3, it's trigonal planar. If there are 4, tetrahedral. If there are 5, trigonal, bipyramidal, and octahedral. if there are 6. This is the first 1, 2, 3, 4, 5 basic structure. From here we can get, within each domain we have multiple shapes, which we are going to learn. Don't worry about, oh my god, this table is so much information. We are going to take up it one by one. Okay? So don't worry about it. This is just a table which gives you a lot of information. Don't worry. We are going to take it one by one. So after you get the electron domain, all we have to do is count the electron domain in the Lewis structure, and that will give you a geometry which is we usually called an electron domain geometry. So say for example, here is, we are taking ammonia, NH3 molecule as an example. And if you draw the Lewis structure of ammonia, this is the structure we get, right? If you count the electron domains around nitrogen, how many we count? How many electron domains we count around nitrogen? 4, right? So 4 means which basic shape that corresponds to? Tetrahedral. Remember that name has linear is 2, trigonal planar, tri for 3, so trigonal planar, tetra 4, so tetrahedron, trigonal bipyramidal, when you have 5 sets. Tri means 3, bi means 2, so 2 plus 3 is 5. So when you have 5 sets, it is trigonal bipyramidal, and then octa means 6, right? So that is how you remember the basic shapes. The number with what name will start with that number. Okay? So linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. In that, this one we say it is tetrahedral electron domain geometry, right? But the actual molecule is not a tetrahedral molecule, because in the actual molecule, when you say the molecular geometry, we are actually looking at the shape of the molecule. And the shape of the molecule include only the bonding atoms, not the lone pairs. So when you think about the shape, we have to envision that parent structure, and we have to remove the lone pairs from the parent structure. Whatever is the resulting structure, that is called the actual shape of the molecule. So once again, ammonia, this is the Lewis structure. We counted this 4 electron sets. So you had a tetrahedral parent geometry. Now among the 4, 1 is a lone pair, right? So you remove that lone pair. You don't visualize that. What do you have in resulting? And that is the molecular geometry. So this molecular geometry, this particular shape is called trigonal pyramidal. Let me show you this molecule, how this works. So ammonia, and we said tetrahedral, right? This is the parent structure, tetrahedral. Center atom with 4. Okay? Now, we said 1 is a lone pair, so we have to make that invisible. Making that invisible means in your mind, take off that 1. What is the shape you get? This is called trigonal pyramidal. So it's trigonal because it is like 3 edges, and look at when you put it on, it's not on the same plane. There is another shape called trigonal planar. Notice the difference between the both. Can everyone see the difference between the both? Trigonal planar is all of them are in the same plane, the central atom as well as the peripheral atoms. Here it's like a pyramid. The center one is like raising up like a pyramid. That is why this is called trigonal pyramidal.
Is that because the other one did not have lone pair?
This doesn't have any lone pair. Yes. This one, all 3 sets are bonding pair. Okay, so that is the main difference. So all the molecular shapes, if you remember these basic shapes, this is the linear shape, trigonal planar, tetrahedral, and trigonal bipyramidal, the one with 5, and octahedral. These are the basic shapes. If you remember these basic shapes, you can derive the shape of any molecule from this. Okay? And as I said, next week you are going to build molecules, so you really get a chance to build them and play with them, so that that shape is imprinted on your mind or on your brain. Okay? We will get a chance. But let's just learn how we get this. So once again, from the parent structure, we have to envision the shape of the molecule only by looking at the bonded atoms. We have to kind of try to remove the lone pairs. Okay? Now, Within, so once again this is showing you the same thing. So this was the tetrahedral structure, the parent structure, and we remove one corner, then we get trigonal pyramidal. This is my trigonal pyramidal structure. Now let's say I had, in the tetrahedral structure, I had 2 lone pairs. Okay, among the 4, let's assume I had 2 lone pairs. So I have to remove 2. If I remove 2, then what is the shape I get? A bent shape. Okay, so tetrahedral can have total 3 shapes: tetrahedral, trigonal pyramidal, or bent. That is only an example. Within each electron domain, then there might be more than one molecular geometry. So we are going to learn that now. We are taking one by one, and we are going to see what are the possible shapes in each domain. So the first one is the linear electron domain. So linear is just 2 electron sets around the central atom. Say that again? No non-bonding electrons. Only 2 electron sets, and they are all bonding. That is the linear electron domain. Okay? And there is only one, linear means there is only one geometry, the linear geometry. Say for example carbon dioxide. That is a linear geometry. So another linear geometry is a molecule with only 2 atoms, like HCl, hydrogen chloride, hydrogen and chlorine. So there is no shape coming from there, right? Just 2 atoms connected together. So that has to be linear. So if you have a molecule with just 2 atoms in it, without saying, the shape is going to be linear. If you have a molecule with more than 2 atoms, and the Lewis structure gives you a central atom with only 2 electron domains, none of them lone pairs, then the structure is going to be linear. And when we say linear, try to remember the bond angle also at this point. Linear will have a bond angle of what? Look at that shape. What do you think the bond angle will be? Bond angle means this is, let's assume this is the linear shape. We are looking at the angle. What is this angle? 180. So linear has a bond angle of 180 degrees. So these basic shapes we will try to remember the bond angles also. Okay? So linear has a bond angle, and everyone understand the linear geometry? What do we mean by linear geometry? The central atom has 2 sets of electron domains, and they both are bonding electron domains. No lone pairs on the central atom. Water is not linear because oxygen has lone pairs on it. So that alters the, so just by looking at the Lewis structure, don't think that if you have something like water, like H2O, O in the middle, 2 hydrogens, you might draw it like this, but that's not the actual shape. That's what we keep saying. Lewis structure is only 2-dimensional, so you will just draw it, the best way possible. But that doesn't give you the shape of the molecule. Shape is 3-dimensional. That is why you have to visualize that.
So that would be a bend.
Water will be bent. Yes, we are going to look at one by one so you will get it clear. So linear, everyone is clear on linear? Right? The central atom has no non-bonding electrons or no lone pairs, only 2 electron domains, both are bonding. So that geometry is going to be linear. Now the next one is trigonal planar domain. This is the trigonal planar one. As we have seen, when you put it, everything is in same plane. So trigonal planar, tri. So that means it has 3 electron sets around the central atom. All 3 are bonding. Okay? So that is the first one says. The number of electron domains on the central atom, that is 3. And all 3 are bonding, no lone pairs on the central atom. Then the actual molecular geometry is also trigonal planar. An example is BF3, like boron. Just 3. When you count this, 1, 2, 3 sets, right? And no lone pairs. So this is a trigonal planar molecular geometry. Now, among the 3 sets of electron domains, let us assume 2 are bonding. 2 are bonding and 1 is non-bonding. Okay? When you draw the Lewis structure, you are looking at the central atom and you are counting, and you see that total 3 sets, but 2 are bonding and 1 is a lone pair. Remember, when we imagine the shape, we have to imagine it without the lone pairs, right? So when you count 3, you are visualizing first, okay, 3 means trigonal planar. So you get that picture first in your mind. Then you are saying, okay, but 1 is a lone pair, so I have to visualize it without 1. Remove 1 from trigonal planar and visualize what is the shape? Bent shape. So trigonal planar can give you 2 different geometries if all 3 are bonding pairs, or in other words, the central atom do not have any lone pairs, then it is trigonal planar geometry. And among the 3, if 1 is a lone pair, then you remove that and you get a bent shape. Now trigonal planar geometry, the bond angle, this bond angle. Oh, I didn't get my pen yet. That is going to be 120. You are right. This bond angle is 120 degrees. I'm not going to focus much on the derived shape bond angles. Actually, this one is I think 119, if I remember correctly. It's a little bit lesser than 120 because the lone pairs take up more space than the actual bonding pairs. So they will kind of push the bonding ones a little bit conical ways. So this is a little bit lesser than 120. What I'm going to do is we will just focus on the bond angles of the basic shapes. Okay? Linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. The derived shapes, let us not worry about the bond angles now. Is that good enough? Okay. No, I'm not asking you to memorize them right now.
I can just make sure most of them out of a circle. That's how they would.
Out of the circle, you will get the basic shapes, but when it is derived shapes, they will change a little bit. That's what I'm trying to say. It's not going to be 360 divided by whatever you see. It's not going to be that way. That's why I said this one is going to be 119. It's not going to be 120 exactly if you look at this one, even though it looks like 120. And as you see the bend shape, there are 2 different bend shape. One bend shape which is coming from trigonal planar, another bend shape which coming from tetrahedral, and they both are not the same. They both have different bond angles. Okay, that is why I said let us not focus right now on the derived bond angles. Let us just focus on the basic shapes. So trigonal planar, everyone has a good picture? Once again, trigonal planar, all 3 bonding, right? Around the central atom, 3 electron domain, all 3 bonding, then it is trigonal planar. If it is a lone pair, then we remove that to envision the shape and you get the bent shape. Okay? So that is the trigonal planar domain. And the next one is going to be the tetrahedral domain. Oh, well, here, this is where that bond angle stuff coming in. So look at the difference in bond angles. Even though they are all coming from tetrahedral, do you see all different bond angles? So this is the basic tetrahedron, like this one. All 4 bonding electrons. So this one you will get 109.5 by dividing 360 by 4, equal. Okay. Well, no, 360 by 4 is 90, right? But when you draw the Lewis structure, the angle will look like 90. Let's say, for imagine, this is CH4 molecule. If you were to draw the Lewis structure, what would you draw? C in the middle, and you would draw like this. This is what you will draw for CH4, right? And this bond angle, this looks like it is 90 degree, correct? But in reality, when you give it a 3-dimension, look at this. This bond angle is larger than 90. This is actually 109.5 degrees. So the basic bond angle of tetrahedron is 109.5. Okay? Now tetrahedron can give you 2 more derived shapes as we have seen. If tetrahedron, tetra means 4. So if your central atom has 4 electron domain, your electron domain geometry is 4. If all 4 are bonded, then your actual shape is also tetrahedron. Now, among the 4, if 1 is a lone pair, you have to visualize it without that 1. then the shape will become trigonal pyramidal. It's just one pyramidal, okay? Not bipyramidal. Trigonal pyramidal. And in trigonal pyramidal, look at the bond angle. The second picture, NH3. It's 107. It's little bit lower than 109.5.
Does it always have a pattern like that? 'Cause that's
There is, yes, there is a pattern. Well, it's not exactly 2.5. Here you will see 2.5, but don't think that 2.5 is a magic number or anything. Okay? Don't follow. Yes, here it is. And then, as we said, this is the water molecule. Look at the picture of water molecule. If you draw the water molecule, you would usually draw oxygen in the middle, hydrogen, hydrogen, and we put two lone pairs like this, right? It's very easy to make the mistake looking at that. Oh, linear molecule. Correct? Because that's what we have drawn. Please start keeping that separate from your visualization. Lewis structure, what you draw is not the actual shape. Actual shape, you have to do this. So you draw this and then you are going to look at the central atom and you are going to count the electron domains. 1, 2, 3, 4. 4 electron domains, right? 4 means the parent structure is tetrahedral. So imagine the tetrahedral and then you are looking at the oxygen. Only 2 are bonding pairs, 2 are lone pairs. That means you have to remove the 2 of them because we have to visualize it without the lone pairs, right? So you remove the 2 and then you get the bent shape. So water is a bent molecule, not a linear molecule. So that is how we are going to do this. So tetrahedron, we will get tetrahedral, trigonal pyramidal and bent shape. Everyone is with me so far? Okay. Now here is the trigonal, this molecule. Look at this carbon. You tell me what is the molecular geometry of this molecule. Look at the central carbon. How many electron domains are there? 3. Right? 1, 2, 3. Remember, double bond counts as only 1. So 3 electron domains. No lone pairs on the central atom. That means which electron geometry? Trigonal planar, which is this. But and with trigonal planar, we would think it is all 120 degrees. Right? Bond angle. Is it actually 120?
No, because a double bond is longer
Dub-
than a single bond.
Yes, and more than that, the double bond has, remember, even though we count it as only one set, there are actually 4 electrons in a double bond compared to 2 in single bond, right? So those 4 will take up more space, and or they will push the other 2 single bonds kind of. You can imagine if this one side, this oxygen side has more electrons in there, they are going to push the other 2 bonds kind of against it. So those 2 will kind of come together and they shrink. They become like 111 and they will get the extra space. Okay, so this geometry is still trigonal. What geometry is this?
Trigonal planar.
Trigonal planar. Yes. Planar, whichever way you say, I'm fine. As long as you have it right. Okay, so tetrahedral electron geometry, we already have seen this. Tetrahedral geometry has 3 shapes. One is tetrahedral itself. All 4 are bonding. Then if one is a lone pair, then you have trigonal pyramidal, and if there are 2 lone pairs, then you have bent shape. We are good so far? Okay, now let us look at the next one, trigonal bipyramidal electron domain. So trigonal bipyramidal, how many electron sets? 5, tri and bi, remember that way. Okay, 2 plus 3 plus 2, tri plus bi. Yeah, it makes sense. So when tri-bipyramidal means it is 5 electron domain. Now in here there are 2 distinct positions in trigonal bipyramidal geometry. One is called axial position, the other one is called equatorial position. Just like on Earth we know we have an axis and equator, the same way. This is the trigonal bipyramidal electron domain. As you can see, there are on the central atom there are 5 electron sets, right? Now, the one which I have used the longer lines with the green, that is called the axial positions, the two axial positions. Okay? And the one around the central atom, just like the equator, this is called the equatorial positions. Everyone see the positions? Make sense? Axial positions and equatorial positions. Right? Okay. Now, usually the non-bonding electrons go to the equatorial positions. They prefer the equatorial positions because when they go to equatorial positions, it will result in a lower energy conformation. And we know that molecules, the arrangement of electrons, they always prefer the lowest possible energy, right? So equatorial position and axial position, equatorial position has a lower energy conformation. And we know that the lone pairs need more space. So they actually prefer the equatorial position to the axial position. We have to keep that in mind when we talk about this geometry. Now, in here we can get 4 different molecular shapes. We are going to see how each of them are. So trigonal bipyramidal, 5 electron domains. Let's say all 5 are bonding, then this is the geometry, trigonal bipyramidal, right? Now let's say among the 5, one is a non-bonding pair. Only one. And we said the non-bonding ones prefer the equatorial position, correct? So among this 5, one is a non-bonding pair and it is on the equatorial position. So for the actual shape, I have to remove one from the equatorial position, right? Removing the lone pair. Now look at this shape. This is called the seesaw shape. Because if you place this, just like a seesaw. Can you see it, Bethany? Can you see it? I'll put it here. Look at this. That is what the seesaw does, right? That is why this shape is called the seesaw position. So when you have 4, 5 trigonal bipyramidal, if you have one lone pair, what you have to remember is axial and equatorial. Which one you will remove? That is why I said in the beginning, lone pairs prefer the equatorial position. So if you are removing a lone pair, that you have to remove from the equatorial position, and that will result in a shape called the seesaw shape. Okay? As everyone has seen, that acts like a seesaw. Now let us imagine we have among the 5, there are 2 lone pairs. So if there are 2 lone pairs, remember again, lone pairs will prefer the equatorial position, right? So we have to remove 2 from the equatorial position. Can you visualize the shape in your mind without looking at the answer? What is the shape? Well, let's visualize this as a T. Okay, T can have a little more longer one, but looks like a T. I know, but you know, in reality, there is no difference between the length of axle. In reality, as I said, there is no difference between the length of, you know, equatorial and axial positions. I put them with different length and different colors so that you can visualize more clearly. In reality, it will be like this. This looks more like a T when the lengths are the same and the color is the same. Okay?
On the bottom.
I'm just going to put them back like this so that you can visualize it more clearly. But when you have 2 lone pairs removed from the equatorial position, imagine that is a T. Okay? So that is what is called the T-shaped molecule. Now, let us say we have 5, the trigonal bipyramidal, the original structure, and we have 3 lone pairs. So 3 lone pairs means all equatorial positions, all 3 equatorial positions are gone. Correct? Back to linear. Only the axial positions are occupied by atoms. So the shape is linear. So that is what the 4 different shapes. Does everyone have a picturization of the 4 once again? So here is our original structure. trigonal bipyramidal, axial positions, equatorial positions. Okay. Now keep in mind, lone pairs prefer equatorial positions. So if there are lone pairs, they preferably take up the equatorial positions. Okay. All right. Now let us start. So all 5 are bonding. Same shape. Correct? Trigonal bipyramidal. Now 1 is a lone pair. So that means I have to remove 1 from the equatorial position. Seesaw. You can imagine, right? All right. Now back to original. Now I have 2 lone pairs. You got the T. Yes. I have all 3 lone pairs. Got the linear. Good enough? So, yeah, as I said, if you go it systematically, it is very easy once you get that. I don't know, Derek, what you did. He said he didn't do well on this. Maybe you were given all the names and all the shapes and just asked to learn.
You wouldn't be able to
Picture all this. I know, that's why I bring them and I show them. Like,
Doing hands-on.
okay, I'm sorry, honey. Here is your chance to learn. Don't worry, after this class you are going to say, hey, I got it finally. All right, now the last electron domain, octahedral. Octa means 6, right? So we have 6 electron domains around the central atom and we have octahedral. So octahedral, this is the parent shape. The central atom has 6 around it, okay? Now all positions are equal here. We don't have any equatorial and axial position with octahedral. It's just all positions have equal importance. Now we can get 3 different molecular geometries from octahedral. Let's try to do again. How do you get that? So here is our octahedral shape. Okay, like all 6. Now if we have 1 lone pair, we have to remove 1. Here it is. I removed 1. Look at this shape. This is called square pyramidal because it's kind of, you can imagine kind of this way or whichever, I don't know how you want to imagine it. Let me put it to you. Square in the bottom and then, you know, one goes like this. So we can call it square pyramidal. Make sense? The other one was trigonal pyramidal from the tetrahedral because we had 3, what do you call this? 3 base or 3 legs and then we had the pyramid going up. Here we have 4 and then the pyramid going up. Okay? So this is square pyramidal and that is trigonal pyramidal. And where did this come from? Which geometry this come from? Trigonal pyramidal? How did we get this? From the tetrahedron. You had tetrahedron all 4, right? Remove 1, you get the trigonal pyramidal. So once again, we had the octahedron. When you remove 1 lone pair, we have square pyramid. Now, let's say we have 2 lone pairs in an octahedron. So we have to remove 2. Look at that shape. Not a cross. It's called square planar because this one was trigonal planar, 3 and in the same plane, right? This is square planar because 4 and in the same plane. Make sense? So these are the shapes. This is all I am teaching today. I am not going to any further on this thing. Let us do practice exercise. Before you do the exercise, does anyone want me to go through this one more time with each geometry? Do you want me to go through this one more time? I can. Yeah. And next week, as I said, remember we draw the Lewis structures in the lab today, right? Next week when you come to the lab, what you need to do is looking at your structure, you are going to count the electron domains, you are going to differentiate between bonding and non-bonding, and then when you look at that, you know the shape now, right? And I'll give you, as I said, each group I'll give you a set of balls and sticks and stuff, and you will make all those molecules so that it is really on your brain how each shape is. That is our plan. Sounds good? All right, let's do 9.2. What is it about? I don't have the book today.
Molecular geometries of molecules with expanded Valence-Shell.
Okay, what are the molecules? If you give me the formula, I can do it. BR F3. Only one? ICl 4 minus. Those are the two? Okay, so for the shape, remember the first thing is we need the Lewis structure. So the first step is drawing the Lewis structure, and we know that. Let's do that. How many valence electrons here? Both are from group 7. So 28 valence electrons here, right? Okay. And who goes in the middle? Of course, bromine. And we have F, and F. Remember, the peripheral ones always have octet. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. How many am I using? 6 times 3, 18, 20, 22, 24, right? I have 4 more. Where will I put the 4 more? On bromine. There is no other way, right? All 28 shown? Okay. Now let us just focus on bromine. Once you have the Lewis structure, we are just going to focus on the central atom to get the shape. So bromine has how many electron sets around it? Only 3? 5, right? So the parent shape is trigonal, which gives you 5. Trigonal bipyramidal. So that is our parent shape. Everyone visualize trigonal bipyramidal. Visualized? Need help? Look at here. Now, we said the lone pairs prefer the equatorial positions, correct? So, how many lone pairs we have there? 2. So, from the equatorial positions, we have to remove 2 and visualize the shape. The T-shaped. So, this molecule is T-shaped.
That's all I want to know.
That's all, yeah? They want both. Yeah, we will do the other one also.
No, I'm saying they want
Bond angle also.
They wanted to know that it was
trigonal.
right.
The parent structure and the original shape. Yeah, of course. To get the shape, you need actually decide the parent structure first, right? It's easy, guys. Once you really get this, it's just step by step and you cannot make a mistake. Shall we do the other one? Okay, ICl4. Again, both are from group 7. So 7 plus 4 times 7, 28 plus 1. So how many total? 34 or 36? 36. Okay. Who goes in the middle? I goes in the middle. Okay. And 4 Cls. And each of them need 6 more. So how many we are showing so far? 6 times 4, 24, 26, 28, 30, 32. That means we need to put 2 on I. 2 sets, right? Okay, now let us look at the I and count the electron domains. How many electron domains are there? 6. 6 means what is the parent shape? Octa. 6 for octa. So octahedron is your electron domain geometry, right? Now, how many lone pairs we have? 2. So we need to remove 2 from octahedral. You have the square planar shape. Got it? All right, then I think we will stop right here. Feel free to come and, if you want. Well, we will stop right here, but I just wanted to show you guys a couple of more things on the molecule when it comes to multiple bonds, actually how the shape will look like. Okay? So here is a molecule C2H4. If you draw the structure, I'm just going to draw it for you. C double bond C and H and H, H and H. This is the molecule C2H4. I made the molecule. This is the C2H4 molecule. As you can see, it is a double bond, right? Now, when you have multiple central atoms, how do we decide the shape? We will consider only one of the central atoms. So, just focus on one carbon here, and there are 3 electron domains on that carbon, and if 3 means what should be the shape? There are no lone pairs, so 3 means trigonal planar. Can everyone see the trigonal planar on that carbon? So even with multiple bonds, notes that it doesn't change. Okay? So that is the trigonal planar one. So if you look at the benzene molecule, which you have seen, that alternating double bonds on carbon, what is the geometry of each of those carbon? Each of those carbon is trigonal planar. Okay? Because if you look at each of those carbon, each of them have 3 electron domains, and they are all trigonal planar. And now another molecule, which is C2H2, acetylene, C triple bond C and H and H. What do you think that molecule would look like? How many consider one carbon, how many electron domains on that one carbon? 2. No lone pairs. So what is the geometry? Linear. Look at the molecule. The triple bond, and it's a linear geometry. So actual shape and the geometry, you can really make them and visualize them. Just wanted to show you the double and triple bonded stuff, that's all. Alright guys, have a good weekend. I'll see you all on Tuesday.